Let's look at this problem. Frida the frog begins a sequence of hops on a 3x3 grid of squares, moving one square on each hop and choosing at random the direction of each hop, up, down, left, or right. She does not hop diagonally. When the direction of a hop would take Frida off the grid, she wraps around and jumps to the opposite edge. For example, if Frida begins in the center square and makes two hops up, the first hop would place her in the top row middle square, and the second hop would cause Frida to jump to the opposite edge, landing in the bottom row middle square. Suppose Frida starts from the center square, makes at most 4 hops at random, and stops hopping if she lands on a corner square. What is the probability that she reaches a corner square on one of the 4 hops? This is a general probability/counting problem. And as I mentioned in many of my other videos, in such complicated problems, we normally want to do casework to finish the counting. And by doing so, we can split the problem into smaller and easier cases. And this is called casework. And in this problem, we'll do the same thing. We'll do the casework. And as to this specific problem, there are 2 other difficult parts. One is to understand the mechanism of hopping, and the other is to understand the stopping time. So let's go over that one by one. For the first one, the mechanism of hopping is very interesting because we only have limited space, and sooner or later this frog will reach the edge and she may hop out of the grid. What happens is this: wrapping around. What does that mean? So in the problem, it gives an example. So I will explain that with this diagram. Suppose we have this 3x3 grid, and she starts from the center. Then she hops up twice. The first hop will land her in here, in the upper row middle square. And the next hop, she will jump out of the grid and then wraps around and re-enters the grid from the bottom middle square. And this is where she lands. That's called wrapping around. So let's make another example. If she hops left twice, so the first time will land her here. And the second time, she hops out of the grid and then wraps around, re-enters the grid from the opposite edge and lands in here. That's called wrapping around. So we have to understand this well enough, otherwise we may very likely miscount the probabilities. Good, so that's the first difficult part. The second difficult part is this. In the problem, it says that Frida stops hopping if she lands on a corner square. And then many students would think that once after she reaches a corner square, let's say after 2 hops, then they will stop counting. That's a very common mistake, because at the end of the day, we need to compare all the possible stopping times, no matter it lands at a corner for the first time after 2 hops or after 4 hops. Therefore, we have to compare things apple to apple, which means that during our counting, even if after she lands at a corner square, as long as that's not the 4th hop, we should let her continue hopping. And of course, after that, she can just hop randomly in any direction. And then in the end, we'll compare all possibilities after the fully completed 4 hops. That's the second trap that this problem set up for many students. Good, so now let's start the counting. And as we mentioned, we want to do the casework. Then what is a good criteria that we split this problem? Some students may think of other ways, but as for me, the most obvious criteria would be the stopping time, right? Just as we discussed the second difficult part. Frida the frog can have different stopping time, right? We call that quoted stopping time. She doesn't really stop there. She'll continue hop randomly. But what matters is what is the first time she reached a corner square. Therefore, let's do the casework by stopping time. So casework by stopping time. So this is so-called stopping time. It's not the actual stopping time. It is just the first time that she reaches a corner square. And then we know that obviously we have 3 cases. That's 2 hops, 3 hops, and 4 hops. Can she reach a corner square after only 1 hop? That's impossible, right? Because she can't hop diagonally. That's what this says. She does not hop diagonally. Good. And before we do the counting for each of these 3 cases, we want to do one more thing. And that is the total number of ways that she can hop around in 4 steps. Since each step is independent of the others, and for each step she can hop in any of the 4 directions, up, down, right, or left. Therefore, the total number of ways that she can hop around in 4 steps is 4 to the power of 4, right? And this number will serve as the denominator in our probability. Good. Now let's come back to the cases. In the first case, she needs to reach a corner square in 2 hops. And certainly for the first hop, she can hop in any direction. That's 4 possible ways. And then by symmetry, we can assume that she just hops, let's say, to the right. Let's say the first step, she jumps to here. Then she has 2 ways to reach a corner square. She can either go up or go down, right? And the same thing for here. If she hops up in the first step, then she can go to the left or go to the right. Then we know that in order to reach a corner square, she has 2 choices to make for the second hop. Then are we done yet? Certainly no. That's what we discussed about the second difficult part, or the second trap that this problem set up. That is stop hopping. So we can't let her just stop hopping. She should continue hopping and finish the rest of the 2 hops. Then for each hop, she can make 4 choices, right, in either directions. So that's times 4 and then times 4 again. This is the 3rd random hop, and this is the 4th random hop. So I'll mark this as the 3rd and the 4th. Good. Then let's look at the second case. 3 hops. I'll draw a new grid of squares. Let's say this is our new grid. For 3 hops, again, she can take any of the 4 directions in the first hop. So this is the first, right? That's the first. Then by symmetry, let's assume that she lands in here after the first hop. Then what should she do now? She can either go back, I'll use a different color. So she can either go back or go out, right? When she goes out, she'll wrap around and lands in here. Are both cases possible? Certainly not. Since she needs to reach the corner square in 3 hops, she can't go back to the starting point, because then she needs at least 2 hops to reach any corner square. Therefore, we know that this is wrong. Only this is good. Then for the second hop, she has only 1 choice, right? So this is the second hop. After that, she lands in here. Then for the third hop, she can either go left or go right. Then we know she has two choices. And again, for the same reason of the same case, in the last or the fourth hop, she can go any direction. That's 4. We need to multiply at 4. Good. Now let's look at the last case. We need a new grid in here. So I'll draw a new grid. So as always, for the first hop, she can go any directions, right? I'll scroll down a little bit. She can go any directions. And by symmetry, let's assume that she go to the left and lands in here. Now she has two choices. She can either hop back to the starting point or hopping out and then wraps around and lands in here, right? So that means she has two subcases. The first subcase is back to center, and the second subcase is wrapping around. Good. Then the number of choice for the second step for the first subcase is 1, and 1 for the second subcase, right? And then let's multiply the possible choices for the third step. When she comes back to the starting point, then the next step, she can again go to any of the 4 directions. And let's assume that she go to the top, right? By symmetry, it's the same thing. If she goes to the top, then at the last step, she can either go here or go here. Then we have times 2 for the fourth step. Then for the second subcase, if she wraps around and lands in here after the second hop, she has two choices. She can either continue to hop to the center. She can't go to the up or down, because otherwise she will end in a corner square in 3 hops. So we will not consider that case. But going to the center is bad, because she only has 1 hop left. She can't hop to a corner square in 1 hop from the center square, right? So this is wrong. That means she has to hop out and then wraps back into this place. Therefore, for the third hop, she has to go out and wrap around again. So that's only 1 choice. And once after that, she can either go up or go down. That's 2 number of choices. Up to now, we've finished the counting of all possibilities that she can reach a corner square in 4 hops. So eventually we need to sum up these numbers. So now let's calculate the probability. So for the probability, we know that the denominator is 4 to the power of 4. And the numerator is 4 times 2 times 4 times 4. That's this first case. And the second case is 4 times 1 times 2 times 4. That's the second case. And then plus the third case. For the third case, we have 2 subcases. One is 1 times 4 times 2. And the other is 1 times 1 times 2. So this is from the third case. All right, now let's complete this computation. So this equals to what? We have a 4 times here as well. This is the first step, right? We almost made a mistake. So then we need to do one thing. We need to cancel the common factors so as to simplify this expression. So we cancel out a common factor of 4. So this becomes 4 cubed. And this 4 cancel out, and this 4 cancel out, and this 4 cancel out. Therefore, we have 4 cubed as the denominator, and the numerator is 2 times 16, that's 32, plus 2 times 4, that's 8, plus 4 times 2, that's 8, that's 2, 8 plus 2, that's 10. So we have a 10. Then we have 32 plus 8, that's 40, 50. So we have 50 over 4 cubed. And then we can cancel out a factor of 2 again. So this becomes 25, this becomes 4 squared times 2. Therefore, we have 25 over 16 times 2, that's 32. Then this is our probability. So now let's look at the choices. 25 over 32. So D is our choice. If you like this video, please give it a like and subscribe the channel. If you have questions, please leave a comment.